All right, I'd like to start in chapter 2, and that's on resistance and components. This is lecture 2. If you look at a piece of conductor, the resistance is defined as, well, this is the equation. Actually, it depends on the 4 different parameters of the variable, if you will. So in general, the resistance R is equal to rho times L divided by RA. And this equation is only valid at 20 degrees Celsius, which is a room temperature, 20 Celsius. If you do the conversion between Fahrenheit and degrees Celsius, if you remember from your physics, the equation is F minus 32, or 180 is equal to C divided by 100. So if you look at 20 degrees Celsius in this equation, you put in 20 degrees and solve this equation for F. Be 180 times 20 divided by 100 plus 32. That gives you about 68 degrees. So when you calculate the resistance of a given conductor, you really have 3 variables at a room temperature. And then we're going to discuss what happens as the temperature changes. So the resistance R, then we've got rho. This is the resistivity, which is a table in chapter 2, or actually chapter 1. They give you the resistivity of a different components. See if I can find the page that it's on. But it's table 1-3. Let's see. They give you the resistivity, so I can look it up. I'll pick it up here. Silver is 9.9, and that's, if we're going to use in terms of feet, we'll talk about it in more detail, the resistivity, how do you calculate it. And then copper is, of course, silver is very expensive relatively. So they use copper, which is 10.37. It has the largest resistivity. So this resistivity actually is defined as 1 over sigma, and that's conductivity. So if the materials has a very good conductor, has a good conductivity, then it has a very small resistivity, so it's a lot easier for a current for flow. So remember, the current is charge in motion. The less resistance you have more flow of electrons, or higher current. So it makes sense if the resistivity of a material is 1 over conductivity of the materials. So that's rho. L is the length in feet, and A is the cross-sectional area in circular mil. And cm, that's not centimeters, that's circular mil, and we'll talk about that to see what is a circle and how the circular mil is actually defined. And then fourth is also a function of a temperature. It turns out different conductors, they have a positive temperature coefficient. So if you raise the temperature, what happens? You free up more electrons. So it's much harder for electrons to move, because due to the frictions and the random motion of electrons, it would slow down the draft velocity of the electrons, which reduces the current flow. So they call that, like copper, it has a positive temperature coefficient. And you can calculate it based on this equation, that R1 is equal to R20. That's the normal temperature, 20 degrees Celsius. That's the value at the room temperature, times 1 plus alpha of 20 as the temperature coefficient times T1 minus 20 degrees Celsius. So if you know the value of the resistance at a room temperature, and then you want to calculate at any other temperature, let's say T1 at 90 degrees Fahrenheit, you must convert that into the 20 degrees Celsius. You cannot mix Fahrenheit, of course, with a centigrade Celsius, so you must do the conversion. And then that will give you, so R1 will be equal to R20, and then plus R20 times alpha 20 T1 minus T0. So you have the positive temperature coefficient. On the other hand, semiconductors and insulators, they have negative temperature coefficients because the resistance value will go down as you increase the temperature in insulators and in semiconductors. Now let's look at the definition of mil. 1 mil by definition is a 1,000 of an inch. So if you take a piece of conductor and look at the cross-sectional area, and look at the diameter, if by definition, then 1 circle mil is equal to area of the conductor with 1 mil diameter. So if you take a piece of conductor like here, and if that conductor has 1 mil, 1,000 of an inch diameter here, D, then by definition they call this 1 circular mil. So the circular mil is the area of a conductor, cross-sectional area, with 1 mil of diameter. So if I go back to the equation for the resistance R is equal to rho L over A, and solve for rho would be equal to R times A divided by L. Now if the resistance in ohms, A is in circular mil, and L is in foot, then the resistivity would be in ohms circular mil foot. And if you look at the tables right here, they give you the resistivity in circular mil, ohms, foot. And that's how you use that unit to calculate the resistance value of a given conductor. Some textbooks, they use centimeters as opposed to foot circle mils. Then the coefficient, of course, would be different. But in this book, we're just going to use, to be consistent with the book, we're going to use circle mil. Now, to calculate the area here in circle mil, then area would be equal to n squared, and n is the number of mils. So all you have to do is to calculate the value of A in circle mils to use an equation for the resistance to determine the resistance value of a given conductor. You need to determine the number of mils in a conductor, the cross-sectional area, and then square it to give you the circle mil. So let's look at an example. Let's say you like to determine the resistance of a 50-yard silver wire with a diameter of 0.004 inch, 4,000 of inch. So here it is. You got a piece of silver conductor. It's 50 yards. Diameter is equal to 0.004 inch. So right away you multiply that by 1,000 to gives you mils. So 0.004 inch is equal to 4 mil. Then you write your equation. The resistance R is equal to rho L divided by A. If you go back to the table 1.3, silver is 9.9 circle mils ohms foot. So you need to plug that in. So from table 1.3 is the resistivity of silver is 9.9, which is in circle mil ohms foot. Multiply it. L has to be in feet, so you need to convert that. 50 yards, each yard is 3 feet, so multiply that by 3. And then for circle mill, you need to determine the diameter in mils, which we already did. It's 4 mils, and then you square it. So again, simply to calculate the area in circle mill, you determine the number of mils and the diameter, just a square. And you can see feet and feet will cancel out, circle mill will cancel out, then you're only left with ohms. So it'll be 9.9 times 150 divided by 16. If you calculate that, it gives you a 92.8125 ohms. Now, you always need to minimize the resistance value, especially the power company and transmission line, or if you hook up a load which is 50 or 60 away. Let's say you have a well and you want to use some kind of induction motor to pump the water or oil or whatever the case might be, and you want to minimize the resistance value, because what happens, you lose power on the line, and then we're going to see later in the next chapter the power is dissipated in terms of heat, and a form of a heat is always equal to the current of the line times the resistance of the line. So you want to minimize the resistance, because currently you have no control over that, because a certain load will require certain current to operate it. And if you notice in big distribution, the power company, they jack up the voltage up to about 765,000 volts, because when you jack up the voltage, the current will go down in the transformer, the power transformer, and then that's just to minimize the transmission losses. And because the power company, they don't charge the consumers, the customers, for the power lost on the line. They have a meter right at your house, so everything is lost on the line between the power company and residential. The power company is actually responsible for, and so they need to minimize that. Let's look at an example. Let's say you have a load located someplace about 30 feet away, and you need a piece of wire, but you got to determine what type of a wire that you need to use, such that you have minimized the losses on the line and also be able to handle the maximum current. The load requires a maximum current of 110 amps, and the resistance of the line you want to limit it to 0.006 ohms, so very small, very close to zero, so again to minimize the losses on the transmission line. And you want to determine what type of a wire gauge you want to use. Well, if you look at the table in chapter 2, it says wire sizes. It's on pages 45. It's AWG, that's American wire gauge, which is a standard. They give it a number, then you have the area in circle mill, and then they give the resistance of each wire in thousand feet, and then they give you a capacity in amps. And here they have some applications and examples. Residential, they use gauge number 10 or 12, telephone number 21 or 22, and so forth. So have different maximum current capacity, and you want to make sure you don't exceed the limit. All right. So for this, so every time you need to pick the wire gauge that you need to hook up the system, or in this case your load, first you go back to this equation and you solve for the cross-sectional area, because that determines your circle mill, and from that you can look it up in the table, the American wire gauge table, to pick up the gauge number so you can be able to put it in. All right, so it's copper, so A would be equal to rho times L divided by R. Rho is 10.37. Again, that's ohm circle mils foot. So you must make sure the length is in feet, which is already is 30 feet. Divided by a resistance has to be in ohms, which is 0.06. So from here you can determine your cross-sectional area in circular mill, which is 51,850. Then you go to the table and you find 51,850 circular mill or something very close to it. So if you look at the table, the closest one to 51 something is number 3. Which is 52,634. If you use that, you should be able to. You always go with a circular mill which is higher than the one you calculated. But the problem is, if you look at the current capacity of number 3, the current capacity, maximum capacity is 85. So, but you need to be able to exceed, not to exceed, the maximum current is 110 amps in that example. Imax is 110 amps, so you must pick the one that at least be able to handle 110 amps, which is number 1. Well, that gives you circular mills of 83,694. So that equation gives you an approximate value. But if there's no maximum, if the maximum current was maybe 70, then gauge 3 would have been sufficient. But if the gauge 3 does not handle the maximum current, then you have to go with the lower gauge, so it gives you higher current capacity. Now let's look at the resistor types. There are 2 different types. One is a fixed resistor, which is 2 terminal. These are mostly carbon composites. And there are variables. There are variable resistors. There are 3 terminals. Fixed resistor are 2 terminals. They use what is called as a rheostat. That's a variable resistor, and then you can also use it as a potentiometer. It depends on applications. So with a variable resistor, it could be a circular or it could be a sliding one like this. If you use A and B, you can use it as fixed. If you take a potentiometer, it says 5K potentiometer. That means it can go from 0 to 5 kilo ohms. If you use either A and C terminal, or you can use B and C terminal, then you can slide this to change the resistance value. But if you use A and B, you use it as a fixed resistor, which is a 5 kilo ohms. So if you need to adjust the resistance value, then you must use either A and C or B and C as a variable resistor. And you only hook up 2 terminals. But if you use it as a potentiometer, then you must use up as a 3-terminal device. The potentiometer, you can use it as transducer, or you can use it as a voltage divider. So for transducer, it could something come in. Let's say it's in case of a circular transducer. If this angle is coming in, and you have to apply voltage here to it, then you can take off the voltage at any point, so you convert the angle or displacement or a position into the voltage. So that's called a transducer. Or you can use it as a voltage divider. A transducer is usually a circle transducer. It looks like that. It's terminal A and B, and C is a rotating arm. You can adjust the voltage output, depends on the angle. Or you can use it as a voltage divider. You apply or hook up the 2 fixed terminals, A and B, to your supply volts. Let's say you have a 12 volts battery, but you want to get 6 volts out of it to do some kind of a loading, some kind of a biasing, let's say in the digital type, or 5 volts. Then you can use it as a potential as a voltage divider. You hook up the fixed point A and B to your constant applied voltage, and then you adjust the level C until you get 6 volts or 5 volts that you need. So it allows you to It's just like if you have a power supply, when you're adjusting the node, what you're really doing is you're picking up the voltage divider rule. We're going to look at this later on when we'll talk about the voltage divider rule, but you can use it as a voltage divider supply. Now, manufacturing, they don't put the value of the resistors on the components itself. They use color coding, which is a standard. Normally, you have a resistor, which is typical ones that are carbon composites, and the one which is closer to the end, you always start from that end, so you hold it with a smaller distance from the first band to the end of the resistor on the left hand side, and then here's a little bit larger on the right hand side. The first 3 digits or 3 bands, it gives you the resistance value. A and B is the least and most significant bits, and then times 10 to the C. The last band is D, is tolerance. We'll talk about that. And then some manufacturers, they have the 5th band, which is E, and that gives you reliability. But typically, if there's no room, you usually see only 4 bands. Now the color coding is black is 0, brown is 1, red is 2, orange is 3, yellow is 4, green is 5, blue is 6, is a good lighter, the number will go up, violet 7, gray is 8, white is 9. Now for A and B, you always see only those colors, from brown to white. Now band C, which is exponent, it could be also gold and silver. Gold is -1, band C only. Silver is -2, and that's band C only. So if the number is, the resistance is less than, let's say, 1, then you got to use band gold or silver, the color banding. Now for the band D is a tolerance. Gold is 5, only 3 bands. Silver is 10, and if there's no band, it's 20%. What that really means, let's look at an example. Say I pick up a resistor from a box, and you hold, again, the shortest one on the left, and you look at band A, B, and C. Let's say that's blue, gray, and orange. Well, blue is 6. B, which is the second band, is gray, that's 8. And orange is 3. So that will give you R is equal to 6, 8 times 10 to the power of 3, which is C. And then plus or minus. The silver, the band D, silver is 10%. So the resistance will be the tolerance of plus or minus 10% of R sub n, and that's a nominal value. So the first 3 bands will give you a nominal value, and then D is a tolerance. For that resistance, there would be 68,000 plus or minus 10% of the 68,000 is 6,800. So the resistance R could be anywhere between 68,000 minus 6,800 to maximum of 68,000 plus 6,800, or 61,200 and less than 74,800. And then a 5th band is E, which is reliability. And what that really means, there are 4 different colors for band E only. If it's brown is 1%, red is 0.1%, orange is 0.01, and yellow is 0.001. What that really means, let's say for this example, let's say you had a band E which was brown, which is 1%. Okay. What that really means, if it's 1%, that means 1 out of 100 resistor will fail to fall within the tolerance range after 1,000 hours of work. Okay. So if you have a resistor in there that's been used for 1,000 hours in your system, then if the band E is brown, then 1 out of those 100 will fail to fall into this tolerance range that we discussed earlier. In that range. Okay. Now, to go measure the resistance, you use an ohmmeter, but you must always disconnect it from the board or from your component. Do not hold the resistance with both hands if you measure it, and you must de-energize the circuit and at least take out one side of the resistor if you want to measure it. Because if you hold it with your two hands, your body has a resistance anywhere from 10 to 100 ohms, depends on the contact of your fingers. So when you do that, you put a resistance in the resistance of your body in parallel with the resistance that you want to measure. And we're going to see later, when we'll discuss the parallel resistors, the total resistance of your parallel combination, actually the resistance will go down if you put them in parallel. Those are different type of resistors with a color coding. Fixed, variable, and then the variables that is rheostat or the potentiometer. And then you can use the color coding to determine the resistance value. Now, the voltage supplies. We also have three type of voltage supplies. Of course, one is a battery. The capacity of the battery is always given in terms of ampere hour rating, which right in the battery it indicates. Well, it turns out that if you look at the temperature distribution of the ampere hour rating of a battery, it's a bell-shaped curve. It will be maximum room temperature, so if you really want your battery to have a maximum capacity, which consequently give you it will last a little bit longer, is to store it at 20 degrees Celsius. If it's below that, that's 68 degrees Fahrenheit, below that it will lose the energy. Above that is also the same. So around 68, 70 degrees. Even cardiologists these days, they say that the best temperature for heart to operate, the optimal rating is about 70, 75 degrees. 70 degrees actually, 20 degrees Celsius. The other source of a DC source is a power supply. And again, power supplies, which is pretty much used every day with every single computers, kind of electronic devices. What you're really having, you have if you look at the outlet, if you look at it on a scope, there's a pure sine wave coming out of the wall, but the DC is really average value of that signal. And you can see if you take an average value, if you take this signal right here and then hook it up to the DC voltmeter, it will indicate 0, because all DC meters are calibrated to read average value of a signal. And the average value of this signal has got plus and minus that cancel each other out, read 0. So in order to get DC voltage out of this AC signal, first you have a circuit that's called wave shaping. Until about 1930 or 40s, they used did half-wave rectifications, which they use a single diode. If you put a diode in here, diode is only conducting when the voltage is positive. When the voltage is reversed, which is negative, the diode acts like an open circuit and is blocking it. So if I put this signal into a diode that's hooked up to the resistor, if I look at the voltage across the resistor, you're pretty much blocking the negative cycle of the waveform. Later on, well, you'll lose 50% efficiency, so there's the best, and as well as the accuracy of resolution in a meter. So they decided the best thing to do is to use a full wave rectification. This is called half-wave rectification. Here, this is full wave rectification. What it really does, instead of 2, you use 4 diodes in the form of a bridge. Instead of blocking the negative part of the cycle, actually flips it over. So you get this waveform right here, which you have a little bit of ripple on it, but it's still very close to DC. And with a simple filter, you can filter it out such that you get a positive and a straight, constant DC output. Now with all filters, so after you filter it out, it looks very smooth DC voltage. Of course, you can have a potentiometer to change the variable, change the level. Some power supplies have a variable power supplies, or maybe 1 or 2 fixed output. Now, what power supplies, you normally have 3 terminals, minus, plus, and the ground, and you can do 3 different connections. If you require only a plus or minus with no ground, then definitely use a plus or minus to give you a plus or minus voltage. If you put a jumper from positive to the ground, and then take this 2 lead to use it as a source, that gives you a negative supply with respect to the ground. Most digital electronic devices, you have to bias them. When you do the biasing of voltage, then it requires a minus potential with respect to the ground as a biasing voltage, and plus. There are some amplifiers you can really be able to bias it with a single supply, but there are some problems, which we, if I have time, we'll discuss that later. It's called output DC offset voltage. And to minimize that, you balance it with a positive or negative biasing voltage. But if you require positive potential, then what you do, you take the negative terminals and hook it up to the ground. And then now you have take this lead and this lead, or one from here, it doesn't matter. That gives you a positive supply with respect to the ground, because with the amplifier circuits, you only have one reference, and that's with the ground of the whole circuit. So everything else is measured with respect to that ground. That's the second type of a DC source. And third is a DC generator. Again, all the AC, the DC generators, if you look at, they really generate an AC signal, and then they've done rectifications either externally, mechanically, or you can do it with the commutators. So you can do it with a solid state, or you can do it with the mechanicals called commutators, and with the brushes and the armature. Now, advantage of DC generator or DC motor is the torque speed is very linear, unlike AC motors or AC generators. It's a lot easier to control. Until about 30 years ago, most of motors were used in control application to control the speed and torque. They were pretty much AC. AC motors, they have a very nonlinear speed torque, so it's much easier, much more difficult to control. The AC, whereas the DC, the speed torque is pretty linear. So as you pick up the speed, the torque is going down. As you lower speed, the torque is goes up. So the motor actually regulates its own torque and speed, and it's fairly easy to control. Now, with all of these sources, there are 2 types. We only, in this course, we're going to look at the independent voltage sources. With the independent voltage sources, they use these 2 symbols, either a circle with a plus and minus, or long bar is short bar, and that indicates the long bar is always positive and the short bar is negative. With these independent voltage sources, they're either ideal or practical. Of course, nothing in nature is really ideal, so we'll always look at the practical voltage sources. We also have what is called dependent voltage sources. Again, we're not going to discuss in this course. Only we'll look into the amplifiers and transistors. We model it with the dependent voltage sources, and they use a diamond shape to distinguish between independent and dependent type of a source. So you can either have a voltage source or a current source. So let's look at ideal independent voltage source. In the case of your battery, that's considered to be ideal. If you look at your battery of a vehicle, let's say it's 12 volts, and you look at the voltage current characteristics. If you're cranking your car, if you're starting up your car, and by the way, the starter in your vehicle is a simple DC motor, and also a series motor, because it gives the highest torque for a minimum amount of current. And that's one thing, that's something that you want. You want to have a maximum current in the starting. so be able to start a vehicle. Now, if you have your headlights on at the same time you're trying to start a vehicle, and you put a voltmeter across your battery terminals, you see the voltage is going to drop, or if the headlights is on, you can see it gets dimmer. What really is happening when you're drawing too much current, ideally when you say is an independent voltage source, what that really means that the voltage is independent of the current that you draw. Ideally, but in practice, practical voltage source, the voltage is going to drop less than 12 volts, depends how much current you're drawing from it. If you got a cheap full cylinder car like mine, it takes about 100 to 130 amps to start out the vehicle. So at that time, the voltage probably will drop to about 10 volts. So you need to come up with a model to account for that voltage drop. So if it was ideal voltage source, you just simply indicate a plus or minus 12 volts, and that's ideal. If it's practical, which is right here, then you need to put an internal resistance in there, because what happened when 12 volts, when you're drawing 100 amps, we're measuring the output right here, it was 10 volts. So therefore, there's 2 volts drop internally, and to model that, if I take 100 amps and multiply it by 0.02, that gives you 2 volts. And we can see that resistance is equal to voltage divided by current, which is the next topic that we'll look at in chapter 3. So the voltage dropped from 12 to 10 when you draw 100 amps. So if you calculate, that gives you 0.02. So you model your voltage source, and that becomes a practical voltage source. Some power supplies, you got 50 ohms output impedance resistance. That's what you put in there. The same thing with the current source. Independent current source, the current, it should stay constant regardless how much voltage is you're drawing from your source, but it actually drops, so that becomes a practical voltage source. But normally there is no such a thing as a current source. You build one using a voltage source, but so it's the best just to look at the independent voltage source and ideal voltage source. Now with the ohm meter, that you're going to measure the resistance, as I said earlier, you take the ohm meter and you put it directly across it, but you want to make sure at least one set of the resistor is unhooked from the circuit. And if you're going to grab it, do not grab both ends of the resistors to measure it, because you put a body resistance in parallel with it. When you're measuring a voltage, you put a voltmeter also in parallel with it. Now if you look at the voltage coming out of the wall from the outlet, if you look at it in the scope, the peak value is about 156 volts. On the scope, what you see is what you get. But if you're using an AC voltmeter, it's going to show 110 amps. I'm sorry, 110 volts. The difference between those two, because the old AC voltmeter to calibrate to read the RMS value, which is effective value of AC signal. And again, we're going to get into that when we discuss AC in later chapter. The reason for that is for the voltmeter to act, remember all the meters, they actually read the average value. So if it's an AC, if you put this through it, then the DC part of it is going to read 0, which is no good. So first thing they do, they full rectify it, just like a power supply. So all the AC meters, they have full rectification in them. And then they look at the DC value here, that's what the meter actually responds to. And the difference between the average value and AC value is about 1.11 factor. So when they calibrate the meter, whatever the meter is reading, going to multiply by 1.11, they're going to mark that off as a proper value on your AC. Same thing with a digital one. Say you have an example. Say you have a 100 volt DC, you put a 1K ohm resistor here, 1K ohm resistor here, and if you put a voltmeter here which is AC, well, 100 volts should divide up equally between 1K and 1K. So if you put a voltmeter, you should expect to read 50 volts. But if it's an AC voltmeter, accidentally you switch to AC as opposed to if you put a DC voltmeter here, it definitely is going to read 50 volts. But if you put an AC voltmeter here, it will read 50 times 1.111, which is 55.55. So you're almost 10% error in your measurements. So you have to be very careful when you do the measurements. Make sure if you're measuring a DC, your voltmeter is on DC, because there's a calibration factor involved, which is hidden with all the AC and DC voltmeters or ammeters. But the scope, it gives you the actual value. Again, what you see is what you get on the scope, but the meters, there's a calibration factor involved. All right, that's pretty much everything in that chapter. We're going to look at a set of homework problems, which I'll have them and forward online. So tentatively, let's shoot for next week. We're going to do all the odd problems also in chapter 2. Right. We'll stop here, and then next time we'll start in chapter 3. Thank you.